Welcome back. In the last couple of classes, we have extensively discussed varieties of topics connected with this course, right from spin physics, chemical shifts, coupling constants, and quantum mechanical analysis of NMR spectra, varieties of spin systems, two spin, three spin, weakly coupled, strongly coupled. We discussed about the spin system nomenclature. We also analyzed simple 1D spectra of varieties of nuclei. We discussed the mathematical thing called transformation called Fourier transformation and arrived at varieties of functions, how to do the Fourier transformation, how they are utilized in NMR spectroscopy. We discussed a lot, and in the last couple of classes especially we did the quantum mechanical analysis of various spin systems, worked out the eigenvalues, eigenvectors, eigenvalues, transition frequencies and type of spectrum, everything for weakly coupled, strongly coupled. In this class we slightly change the topic because in a short while from now we have to discuss more about product operators, more about how the chemical shift couplings will evolve in different pulse sequences. We need to understand the pulse sequence, especially if you have to introduce polarization transfer techniques, varieties of things. So, in all these things, one important point which we need to understand is we commonly use what is called a pulse phase and a receiver phase. This of course I should have introduced when I did the when I discussed the 1D NMR spectrum, because I did not want to discuss at that time, because this relevance of this is going to be seen in next couple of classes. And of course regarding the pulse phase and the receiver phase, little bit in not though in detail, little bit we discussed in the previous class, previous course also. But nevertheless you must know what is a receiver phase, you must know what is a pulse phase, which are very often used both understanding the behavior of the magnetization by the vectorial diagram, or we have to use it for understanding the product operators, where we have to show when you apply different phases, different axes, how it behaves. So, I will today discuss more about pulse phase and receiver phase. Okay, let me start with what is an RF pulse. Of course, it is a pulse NMR. We are going to apply a RF pulse, and then in the very first class, as I told you, the magnetization which is a thermal equilibrium which is going to be disturbed, it create a non-equilibrium situation, bring it back to x axis or y axis, and this magnetization goes back to z axis by decaying in the xy plane, inducing an EMF in the receiver coil, which we are going to collect as a function of time and do the Fourier transformation to get the spectrum. This is in short we discussed at stretch long back. So, when we applied RF pulse, of course we discussed about the transitions from different energy levels, that is only a layman way, but in principle that is not very 100% a correct way of explaining the NMR transitions, NMR resonance, but this is the way to understand how the magnetization behaves in different pulse sequences we apply, we will try to understand. So, RF pulse, of course what we are going to use is a rectangular pulse in NMR. Most of the time we use a rectangular pulse. And what is the power of this pulse? Of course, this is the width of the pulse, this is called pulse width. Normally sometimes they use PTP or some width, whatever the way we define. And the power of the pulse is somewhere between 500 to 300 watt, and sometimes we in a high power spectrometers people can go up to 1K, it's very rarely, but 300 to 500 watt is generally what is used in some solid state NMR spectrometers, where you want to do broadband spectrum, we want to get broadband spectrum with high power decoupling, etc. And the width of this pulse is about 10 to 15 microsecond. Remember the 90-degree pulse, in the previous course we discussed a lot. 90-degree pulse in proton, for example, is anywhere between 5 to 6 microsecond approximately. It can be slightly low or it can be high depending upon the type of probe you are using. So, 180 pulse is double of this, 270 pulse is triple of this, 460 pulse is 360 pulse is 4 times this. Like this, width of the pulse can be utilized, and then we say what is a 90 pulse, what is a 180 pulse, what is a 360, 270 pulse, everything we discuss. Now we have to understand something more about this thing, about the phase of the pulse. And of course another thing important is to know when I am applying the pulse in a direction perpendicular to the magnetic field, this is the magnetization. Here x axis and here is, that is a y axis. Magnetization is here, and I tilt it by applying a radio frequency pulse in a x axis. Fine. What is the pulse frequency which you are going to apply? The frequency of the pulse, it should be in the Larmor frequency to create a non-equilibrium situation to tilt the magnetization from z axis to x axis or y axis. This is very important. Okay. Now, RF is a short pulse, a short burst of pulse. The width and the power of the pulse determine how much of magnetization is tilted from the z direction to xy plane. Please understand, magnetization is here along z axis. If I have to shift it to x axis or y axis, I have to shift by 90 degree. And correspondingly, depending upon the RF power and the pulse width, I can tilt it here. Then the maximum magnetization is the xy plane when I bring it back to x axis when the receiver is sitting here. Or if I tilt it only by 5 degree, and you take the projection of that in the x axis where you are having a receiver, let us say, put along x axis, then the component of the magnetization is very small. So, the width and the power of the pulse will determine the how much of equilibrium magnetization you are tilting from z axis to xy plane. And this can be discussed and understood by a simple equation called gamma into B naught over T, gamma into B naught into Tp is what is called theta. Theta is a flip angle, angle by which you are tilting the Z magnetization, equilibrium magnetization to x, towards x or y axis, and gamma B1 is the power, Tp is the width of the pulse. So, what it means is, if you can manipulate power and the pulse width in such a way, you can tilt the magnetization by any angle you like. You can tilt it by 1 degree, 0 degree, 360 degree, whatever the angle you want to do, you can just manipulate by manipulating the RF power and the pulse width. This is a very important thing, you can do that. Now, I will take an example. I have the gamma B1 Tp is equal to pi by 2. Magnetization initially is along z axis. I am going to apply a 90 degree pulse. What it means is, I manipulate in such a way the power and the pulse width that theta becomes 90 pi by 2. That means, the magnetization which was along z axis, I can shift it to one of the axis. How I shift which axis I will discuss later. Let us say I shift it to x axis, the difference is 90 degree. So, I have shifted the magnetization from z axis to x axis. The pulse and the width of the power which we use to tilt this magnetization by 90 degree is called a 90 degree pulse. The 90 degree pulse is the one which tilts the thermal equilibrium magnetization which is along z axis either to x axis or to y axis. So, it is called a 90 degree pulse. Okay. I can determine the 90 degree pulse. In the previous course we discussed how to find out the 90 degree pulse. Let us say I know the 90 degree pulse, I double it. What is going to happen? Let us say 90 degree pulse is 5 microsecond, I will make it 10 microsecond. Then what is going to happen? The thermal magnetization which was along z axis will go further down, it will take into minus z axis, that is called 180 pulse. If from here z axis you tilt it to minus z axis, that is a 180 pulse. You can take it further, you can bring it here, this is 270 pulse. Take it further, instead of 10 microsecond use 15 microsecond, bring it here, use 20 microsecond, then you take it back to z axis. What did you do? The magnetization which was along z axis, we tilted like this, brought it back and then took it back to z axis. We made the magnetization to go round along the xy plane. From x, let us say you apply the pulse along y axis, you are rotating and along this xz plane. It goes round and round. You do not have to stop at 360, you can apply 720, make it undergo 2 rotations. So, you can make the magnetization dance to your tunes. All you require is the RF power you should know and the width of the pulse you know. You can manipulate these two to tilt the magnetization to any direction, any axis at any direction you want. As a consequence, amount of magnetization which you are going to control, which you are going to get it, will be controlled by this pulse. So, the direction of tilting of the magnetization always follows a right hand thumb rule. This is a very important rule we should remember. Direction of the thumb is the axis of application of the pulse. For example, I consider, let us say the magnetization is along x axis or let us say z axis. Now I am going to apply a pulse along x axis. From z axis the magnetization is tilted towards x. This is x, this is y, and this is a plus y, this is minus y. So if I apply a 90-degree pulse along x axis, the magnetization which was along z axis will be tilted to minus y axis. So remember, the direction of the thumb is the axis of application of the pulse, and curly fingers will indicate the direction in which the magnetization is tilted. This is a very important thing. Okay. Now we have to understand something about what is called the phase of the pulse. Phase is defined by the starting point of the sine function. For example, this is a sine function, starting point is 0. It starts with 0, increases to the maximum and decreases further, and let it like this: starting at 0, the amplitude increases at first from 0 to maximum. That is called 0 degree phase. That pulse is called 0 degree phase pulse. Initially start with 0, rise to the maximum from 0. Alternately, it starts with here 90 degree, decreases further to 0. That is called 90 degree phase. You understand? This is 0 degree phase, this is 90 degree phase. Now starting with 180 here, it decreases fast to maximum and then go up. It decreases 0 to negative. It is called 180 phase. Or start at 270 like this, go up negative, from negative peak, go to the negative side from here to here. That is called 270 phase. So remember, the phase of the pulse is defined from its starting point. Here it is a 0 degree phase pulse, 90 degree pulse, 180 phase pulse and 270 pulse. So hereafter we will be talking about the phase of the pulse: 0 degree, 90 degree, 180 degree, 270 phase. Diagrammatically, it depends upon the starting point of the sine wave. Okay. And depending upon the pulse phase, you can put the magnetization vector, that is the in the any axis you want. The B1 vector which you are going to RF power which you are going to apply can be along x axis, along y axis, along any axis, minus x, minus y, plus x, plus y, any axis I can put. The RF vector, the second RF pulse which you are going to apply, I can apply along this axis, this axis, this axis, any axis I can apply. I can put the magnetization vector, B1 vector, not main magnetization, B1 vector to any of the axes. I can play with it. For example, if I apply a 0 degree phase pulse, that means I will say the B1 vector is along x axis. Okay, pulse is along x axis. 0 degree phase, pulse is along x axis. 90 degree phase, B1 vector is along y axis. That means initially 0 phase pulse is here, 90 degree phase it is here, y, and then 180 phase is here, minus x, and 270 pulse is 270 pulse is here, minus y. Imagine in a 3-dimensional space, I am going to apply 90 degree pulse along here, x axis, it is a 0 degree phase pulse. Here it is a 90 degree phase pulse, it is along y axis, and 180 pulse is along minus x axis, 270 pulse is along minus y axis. So this, depending upon the phase you are going to apply, the B1 vector can be at x axis, y axis, minus x axis or minus y axis. This is an important concept you should remember. The phase of the pulse puts the B1 vector in different axes. We should always not forget, 0 degree phase pulse puts along x axis, 90 degree phase puts B1 along y axis, 180 phase puts B1 along minus x, 270 along minus y. These are very, very important. I can control the effect using the effect of the pulse, this vector. So we can also change the amplitude of the pulse and also adjust the length of the vector. This changes the strength of the magnetic field that represents B1 field. I can vary with the pulse amplitude and make sure that magnetize the vector, B1 vector, which let us say I am going to apply RF pulse along x axis, 0 degree phase. What is the length of this B1 vector? It can be this much, and it can be very large. This can be controlled by amplitude and power of the pulse. I can vary this one. So the effect of the RF pulse we will try to understand now. what is the RF pulse effect. The magnetization vector rotates in a plane perpendicular to the B1 field. Remember, the magnetization vector rotates in a plane perpendicular to the B1 field. For example, imagine this is x axis, okay, this is y axis, this is z axis. I am going to apply a pulse along x axis in a direction perpendicular to this, means in the yz plane. The magnetization rotates in the yz plane. If I am going to apply a pulse along x axis, direction perpendicular to this is x, this is z. So, that means the magnetization rotates in the xz plane. So, magnetization vector rotates in a plane perpendicular to the RF pulse you are going to apply. Your RF pulse B1 field I am going to apply in one direction, in a direction perpendicular to that, in that plane the vector keeps rotating. Okay, we will understand these things as we go ahead further. So, it is the axis on which we are going to see the magnetization rotates. That is the important thing. I am going to apply a pulse along z axis, means I am rotating the magnetization along, let us say I consider here. I am going to apply RF pulse along this axis, means I am rotating along this axis, and the rotation in a plane perpendicular to the RF pulse axis. The concept should be very clear, then only we will understand more as we go ahead about the pulse sequences. So, I am applying a RF pulse here along, let us say y axis. That means the rotation is about y axis and the magnetization rotates in a plane perpendicular to y axis, that is in the xz plane it rotates. Okay. The precession frequency is similar to the precession frequency in the main magnetic field. When you apply RF field, it is a magnetic field. I will make this pin to rotate. As I said, I am applying along x axis and make it to rotate in yz plane. But what is the rotation frequency? This is again given by gamma into b naught over 2 pi we gave. Here it is B1. B1 is the RF power. This is much smaller than main magnetic field. Main magnetic field is of the order of several Tesla, 5 Tesla, 10 Tesla, like 20 Tesla, like that. But here very small, okay, very small. Okay, this. Now we will go to the 90-degree pulse on different axis and the precision. I am going to apply a 90-degree pulse, let us say, on plus y axis. This is y axis plus y and this is x axis in a direction perpendicular. They are all orthogonal to each other. What do you mean by telling applying along plus y axis? When I apply this axis, my pulse is along plus y. Put the thumb in this direction, thumb in the direction of plus y. Magnetization was along z axis. The curly finger tells you have to tilt, curly finger shows the direction of tilting. So, magnetization, you apply RF pulse along y, magnetization which was along z will be tilted back to the x axis, it will be tilted towards x axis. So, in a direction perpendicular to it, it is going to be tilted like this. So, then what will happen? It starts rotating in the xz plane, it starts precessing in the xz plane. This concept should be very clear, because these are all very important to understand the behavior of magnetization in different pulse sequences. So, in the simple logic, now we take the other example here. For example, I come here, I am going to apply a radio frequency pulse along minus x. Of course, this is x axis towards me and opposite to me other direction is minus x. I am applying along this axis. So, put the curly finger that side. Then magnetization which was along z, it has to move toward this side, right side. So, from here it moves toward the y axis. The curly finger is telling me, if I put along minus x axis, the curly finger tells me magnetization should move towards plus y axis, because this is my x and that is minus x. Along minus x if you apply, you are bringing it to plus y axis. Then what will happen? It will, because you are applying RF pulse along x axis, that means the rotation is along x axis, but the plane of rotation of the magnetization, the plane of precession of the magnetization is yz plane. These are the important concept you must understand. So, if the magnetization is tilted to xy plane, it is a 90-degree pulse. If it is rotated to minus z axis, it is 180 pulse. If it is rotated to 360 degree, it is a 360 degree pulse. So, you have to define what is the pulse. When we start talking about a 90 pulse, depending upon whichever the direction you are going to apply, whether x axis or y axis, minus x axis, minus y axis, you are tilting in a direction in if I am applying on x axis, it may be tilted to y axis or minus x minus y, depending upon you adopt that right hand thumb rule. And now if I apply here, it can be tilted here, tilted further to by 180 pulse, and I can make it to go around completely one rotation by 360. So 180 degree pulse inverts the population of the spin states. If I am going to go here 180 pulse brings the magnetization from z axis to minus z axis. It will invert the populations, and remember, my 180 degree pulse and 360 degree pulse will not give any signal. Only magnetization in the transverse plane gives the signal. That will only induce the signal in the receiver coil. See, I am having a receiver coil kept here. Remember, in the very first course, in the previous course we explained, this is the direction of magnetization, this is the direction in which you apply the RF field, your receiver is in a direction perpendicular to it. All the three are orthogonal to each other, that is why we have been discussing. You understand? So, now you have got a receiver here, you bring the magnetization from plus z to minus z here, you do not see any signal. So, 180 and 360 pulse, same way you go back to z axis, you do not see any signal. So, 180 degree and 360 degree pulse will not give signal, you will not induce EMF in the receiver coil. Only transverse magnetization here induces EMF, that is what is detected. So, you must, if your receiver is in the x axis or y axis or minus x minus y, the magnetization should be in the xy plane, it should be brought back to xy plane, that is a transverse plane. And maximum intensity you get in 90 degree and 270 degree, it is, that is also we discussed. You bring the magnetization maximum here, and if this is your receiver coil, you get maximum vector is here, length of the vector is maximum. You take the cosine projection of this cosine of this magnetization, it is larger here, very large value, full magnetization is here. Or you take it here minus 70, still it is maximum, but in the opposite direction. So, only 90 and 270 gives you maximum signal intensity, 180 and 360 degree pulses give you 0 signal, no signal will be seen. The phases of the pulses are defined by the axis in which we are applying. This is another important thing I told you. Already I told you 0 degree phase is along x axis, 180 phase is along y axis, 270 are minus x and 360 along minus y. Okay. But we can define like say pulses and phases like this. The pulses are defined by their phases. If I apply 90x pulse means I am applying the 90 degree pulse along x axis, that is a convention. If I say I have a 90x pulse, it means in the direction x axis I am applying a 90 degree pulse. What I am trying to do now? I am rotating the magnetization along x axis in the x axis. So, rotation of the magnetization is in the x axis, but in the direction perpendicular to it is the yz plane, that is what you should remember. So, now 90 degree y pulse, 90 degree y pulse means 90 degree pulse applied along y axis. Similarly, I can apply 180 x pulse, 180 pulse along x axis and 180 y pulse is y pulse 180 along y axis, and you can follow the magnetization trajectory depending upon where you are applying the pulse and what is the degree of the pulse you are applying. That means how much magnetization you are tilting, with that you can follow the trajectory of magnetization. I told you already, magnetization is along the x axis, z axis, apply 90 pulse along x axis, then you are tilting it in the transverse plane. Since the rotation is along x axis, the magnetization rotates in the yz plane in a direction perpendicular to it. Instead of 90 degree I tilt by small angle, then it can rotate in a different way. So, that means you can follow the trajectory of the magnetization depending upon how much of the magnetization you are tilting and in which direction you are applying the RF pulse, which axis you are applying the RF pulse. Let us see the example like this. Now, 90 degree y pulse, tilt the magnetization to x axis. True, magnetization is here, this is the thumb, you put the thumb here and this is the direction. If you take like this, magnetization start tilting towards x axis. Correct. 90y pulse tilts the magnetization to x axis, and 180 pulse continues further, takes it to minus z axis, and 270 pulse takes it further to minus x axis, and 360 pulse of course takes it to z axis. So, what are you doing now? Exactly what I said. You apply a radio frequency pulse along a particular axis, that is the axis of rotation of magnetization, and it rotates in a plane perpendicular to it. So, that means it is rotating in the xz plane. You apply a RF pulse along y axis, you are rotating in the xz plane. This is a point which you have to be very, very clear. Okay. So, now we can understand rotation of the magnetization and different axes, how it rotates when I apply different pulses, what is the way it rotates, we will understand. What is equilibrium magnetization? It is always along z axis. Okay. Now, 90 degree x pulse brings the magnetization to, I am applying a 90 degree pulse, where does the magnetization comes? Minus y axis. See, it is tilted to magnetization. This was the red arrow is my magnetization. I am applying the RF pulse along plus x, it is tilted to minus y. Correct. Now, I am going to do one thing. I apply 180 pulse. 180 pulse width I increased double. I doubled it. Then magnetization is shifted to minus z axis. I took it further. From here, I brought it here and I took it here. Now, I am applying a 270 pulse along x. What I am doing? Increasing the width more. Then I take the magnetization here. It comes here. Okay. Now, I apply 360 pulse. If width is even larger, it is 4 times an 90 pulse. So, magnetization undergoes one full rotation, comes back here. So, what I did do? I am rotating magnetization if you are applying here and started rotating like this. Okay. Depending upon where you are applying, and if this is the x pulse, this is the x axis, y axis, z axis, I am rotating like this. Clockwise rotation you can do, rotation of the magnetization about y z axis, in one direction it rotates. You can also apply the pulse along negative axis. That is the interesting point. Why you have to apply always only on plus x or plus y? You can apply on negative axis also. Then they are called accordingly minus 90 minus x pulse, 90 minus y pulse, 180 minus x pulse, and 180 minus y pulse. You can also apply pulse along negative axis. Okay. These nomenclature define the phases the pulse applied along negative axis. You remember, for the positive axis it is 90 plus x, 90 plus y, 180 plus x, 180 plus y. If you apply along the negative axis the same degree pulse, same 90 degree, 180 degree, but you have to define as represent like this 90 minus x, 90 minus y, 180 minus x, and 180 minus y. This is the way we are going to define. So, what happens if the pulse is applied minus x axis? A 90 degree pulse along x axis will tilt the magnetization to y axis. But we can see now 180 pulse along minus x will tilt to minus z axis. 270 pulse along minus x will tilt to minus y axis. 360 minus x will tilt to again take it back to z axis. So, what did you do? You rotate the magnetization in the yz plane. Let us see what is happening. Minus 90 minus x I am applying. So, you bring the magnetization to plus y axis. Apply 180 minus x, take it to minus z. Apply 270 minus x, take it to minus y. Apply 360 minus x, you are taking it back to z axis. What did you do? You created anti-clockwise rotation about the yz plane. You understood the point. See, one case you can make the magnetization either way, you can think of it. You can make the magnetization to go clockwise like this, you can make the magnetization to go anti-clockwise like this, depending upon which direction you are going to apply the pulse. If you know whether you are applying a x axis or y axis or like plus x or plus y or minus y, accordingly you can tilt the magnetization and make the magnetization to rotate either 20 degree, 270 degree, 180 at 360, either clockwise or anti-clockwise. This is the beauty. So because of this, we can play with the pulsars, play with the phases with the pulsars, apply along different axes and make the magnetization to behave the way we want. And this concept is very much important to understand the behavior of magnetization in different pulse sequences. So now since the time is up, what I am going to do is I will stop now, because I will discuss about the rotation about y axis, how the magnetization behaves, and then afterwards we are just talking about the magnetization. It is only a pulse phase. Now what happens if I am receiving the signal, what happens? That we have to understand receiver phase. And then how the magnetization evolves under chemical shift, under coupling constant also we will discuss. So next class we will discuss more about the receiver phase, everything. Today I was telling you something about what is called a pulse phase. Pulse phase, and I also showed you what is a phase of a pulse, what is a 0 degree phase, 180 phase, 90, 270 phase, and all those things I explained to you. That depends upon the starting point of the sine pulse, sine wave. And I told you magnetization which is tilted to 90 degree by any RF pulse is called a 90 pulse. 90 pulse can be along x axis or minus x axis, plus y axis or minus y axis. The direction in which you apply RF pulse is the rotation axis. And the magnetization always precesses or rotates in a direction perpendicular to the axis of axis in which you are applying RF pulse. I am applying the RF pulse along x axis, then you make the magnetization to rotate along yz plane. I apply the magnetization along y axis, you make the magnetization rotate along the xz plane. And again, depending upon whether you are applying plus x or minus x, you can make it rotate clockwise or anti-clockwise. Similarly, whether you are applying pulse along plus y or minus y, you can make it rotate clockwise xz in the xz plane or rotate in the anti-clockwise. So these are some of the things which are concepts are very clear, should be very clear. We have to understand these things to understand the behavior of magnetization in different pulse sequences as we go ahead later. So we don't discuss every pulse sequence, at least one or two, especially when you want to understand product operator, how it behaves. This type of phase of the pulse and receiver pulses, especially in understanding phase cycling, is very important. So that is why I wanted to introduce this. In the next class, we will continue with the pulse phase and receiver phase and different rotation, and also how evolution of magnetizations and discuss further. I will stop here. Thank you.